Hello everyone, this is Mr. Martin and we are going to be continuing to solve problems with the volumes of solids of revolution. Now, last time we put a video up in which we found the volume of rotating the solid created by the area between the graphs y equals x and y equals x squared about the x-axis. This time we are going to be working with the line y equals x. So if we go to the next page, take a look here. I still have the same graph, the graph of y equals x squared and the graph of y equals x. But in this case, we're going to rotate it about the line y equals x. Now this makes things a little bit trickier. So usually the axis that we rotate about, we're going to want to find the radius between that axis and the line that we're rotating about that axis. In this case, it's the distance between the line y equals x and the line y equals x squared. Now this can be actually a little bit tricky. If I take any point on this line x and y, I want to find the shortest distance between that point and another line. Well, this is going to require a little bit of math. And so what we use for this is, and I'm going to draw it right here, is the distance equation for the distance between any point and a particular line. Now, what we have is the equation of the line. In the standard form, it's basically x1a plus y1b plus c, absolute value of that, all over a squared plus b squared square root, where the standard line that we have is ax plus by equals 0. Now, of course, our line that we're going to is the line y equals x. So with the line equals y equals x, we have a, b, and c values of equal to -1, 1, and 0. So taking that into consideration, I can now write the distance as a little bit of a side note here, because I'm going between 0 and 1, and I can see that the distance is always going to be positive, I need not worry about the absolute values. So what I can write is my new equation, plugging in numbers for x, for a, b, and c, I end up with negative x1 plus y1 all over, a is 1 and b is 1, so a is -1, so it's going to be the square root of 2. So that's going to be the distance between the two lines at any time in terms of x and y. Now I want everything in terms of one variable. So my y1, however, because y1 always falls on the line y equals x squared, y1 is just going to be x1 squared, isn't it? So I can rewrite this as negative x1 plus x1 squared all over square root of 2. So that now is going to be the distance between the lines, which is also the radius when I rotate this graph all the way around, isn't it? So it's going to be the radius of a little disk that I can make And picture this whole graph rotating around, and how the disks are going to travel all the way from 0 all the way up here, but they're going to be going this way, aren't they? Normally we would travel along the x-axis, so we actually have to translate that. Well, this happens to be a very convenient way. The distance of this line from here to here is just the square root of 2, isn't it? Because of the Pythagorean theorem, and we also know that the distance 1 squared plus 1 squared is 2, so square root of 2. So now we can make an integral. So let's go ahead and take a look at the next page. I still have my graph up here to kind of show you what we're doing. We're still rotating it around. It's just a smaller version. We're taking it from the square root of 2 to 0. So if I want to make a new integral, first of all, let's write the distance to make sure I know, keep that in mind. And again, I'm going to write it as this way: x squared minus x over the square root of 2. So my new integral is going to be the integral between 0 and the square root of 2, okay, of the radius squared. Pi r squared is the area of that circle, so I can put pi on the outside of the integral sign because it's a constant. Pi times r. R is the distance, so x squared minus x over square root of 2, quantity squared times my little change in distance. Well, I can rewrite this integral: 0 square root of 2. When I multiply the 2 on the bottom, when it gets multiplied by itself, the square root of 2, it ends up just to be pi over 2. And the top portion of this is a square, so it's just going to be x to the 4th minus 2 times the quantity of the middle, which is going to be x to the 3rd, plus the end term, which is x squared, all to the dx. Integrating this, now I have pi over 2 times the quantity, x to the 5th over 5, that term, minus 2x to the 4th over 2, which is x over 4, plus x to the 3rd over 3, evaluated between 0 and the square root of 2. Well, the 0 terms are just going to give us nothing, so I can rewrite this as pi over 2 times square root of 2 to the 5th. Oh boy, what is that? Well, square root of 2 to the 4th is just 2 times 2 is 4, so it's 4 square roots of 2 over 5. And square root of the 4th is what? Is 4. So 4 over 4 is 1, so it's just going to be minus 2 for that term. And lastly, we have the square root of 3, or excuse me, square root of 2 cubed, so it's plus 2 square roots of 2 over 3. From here, we can just combine like terms. So let's see what we have in combining like terms. I'm going to write it up right underneath the white. I still have pi over 2. I can combine the 4 square roots of 2 and the 5 and the 3, so that's going to be a common denominator of 15. So it's going to be 12 square roots of 2 over 15 plus 10 square roots of 2 over 15 minus just 2. We'll rewrite it like that. So I end up, if I distribute the pi through, I'm going to end up with 11 pi square roots of 2 over 15 minus pi as our volume. And again, that's the volume of taking the graph of y equals x squared and rotating it about the graph of y equals x. Quite a difficult problem.